Bismillahirrahmanirrahim. Assalamu alaikum. How are you all? I hope all of you are doing well and staying safe. In our previous lecture, we discussed how images are stored in computer, how images are digitized and stored in computer. We talked about the vectors and bitmaps, and then we learned how to calculate the size of a bitmap file. Today we are going to do the same with the sound and try to understand how the sound is going to be stored in the computer. Look at this representation of a sound wave. You might have seen that on different audio equipments, sound animation. By looking at this, you might see that the sound is an analog quantity. Analog means it's a physical quantity which is actually measured, and it can have any value from a continuous range of values. The difference between digital and analog quantity is that you can actually count the digital quantities. Digital quantities have discrete pauses in them, but analog quantities are actually continuous and they are not counted, they are actually measured. The natural quantities, the physical quantities we encounter in our daily life, like heat and sound, time, you can consider all of them analog, but we have developed equipment that can convert that analog quantity into a digital quantity. When a mic is actually collecting the sound waves, those sound waves are actually fed into a sound encoder. They are amplified a bit before that, but then they fed into a sound encoder. A sound encoder actually have two components in it. One is a band limiting filter, which removes all the high frequency sounds that can't be heard by the human ear. You might remember that the audible frequency range of the human ear is uh, 0 to 20,000 megahertz, I guess. And any object which is generating sound wave may generate less than that, and beyond that means a sound generating object may generate the sound waves more than 20,000 hertz, the ultrasonics. But there would be no point in coding that. But because if we try to store that, human ear will not be able to hear it, but it will consume the space in the file storage, and it will also increase your sampling resolution as well. So, and cause problems in your encoding of the sound. So band limiting filter actually limits the frequency from 20 to 20,000 hertz, which is the audible frequency range. Then you have an analog to digital converter, or an ADC, that converts the analog data into digital data. Now, how this is done? The conversion of the analog data to digital is actually done using this diagram. I would try to help you understand this. The red line is actually a sound wave, and on that sound wave, we have made a graph. The graph is actually showing us two values, the amplitude of the sound wave and the time, because What the computer is trying to record is actually the amplitude of the sound wave we are interested in. What's happening here that this analog sound wave is plotted onto that graph, and wherever it is actually going through the exact amplitude point, we are able to get the exact reading. Look at the point number 1 and 4. You can see the wave is actually passing through the amplitude points, exact amplitude points. But if you look at the 5 or 6, the wave is passing somewhere between the amplitude points. So in that case, we would have an approximate reading of the amplitude. In the case of 1 and 4, we would have an exact reading of the amplitude. To get the exact reading, we need to increase the number of samples that we are storing. Currently, you can see that we might have a little around 50 samples. Every intersection of time and sound amplitude is exact sample reading. So we have around 50 roughly samples on this graph. But when we are actually recording the sound, we try to get 44,100 samples per second in most cases, which is the average quality sound. We try to get 44,100 samples per second, means we try to record the sound's amplitude 44,100 times in 1 second in order to get as many accurate reading of the sound as possible. Getting the exact sound reading is much more likely if you are taking more samples, and it gets less likely if you are taking less samples. After we have done sampling, we can actually plot that wave onto the graph, and this graph can actually store that sound wave in the digital uh, data, the XY coordinates of the points of the graph, and we can regenerate this sound wave using those XY coordinates again on that graph, which then a speaker can use to regenerate the sound wave. There are some important terms in this. First one is sampling. Sampling means that you're just recording something at regular intervals of time. In this case, we are actually recording the amplitude of the sound wave. Sampling rate means how many samples have been taken per second. Previously, we used to have 33,600 was a manageable sampling rate. But nowadays, usually the sound recording is being done at 44,100 samples per second rate. Right now, while I'm talking, my sound is being recorded at this sample rate. And then you have sampling resolution. You might remember the bit depth concept from my previous lecture. The number of bits used to store each sample. The sampling resolution is just the same. Consider a sampling resolution of only 2 bits. 2 bits means you would have only 4 combinations: 0, 0, 0, 1, 1, 0, and 1, 1. That is going to mean that you are able to only store 4 samples. Now let's consider the sampling resolution of 3 bits. In 3 bits, you would have 8 different combinations. So that means you can actually store 8 different samples. The sampling resolution I was mentioning, 44,100, actually requires 16 bits, because 2 raised to power 16 would be 65,536. So to store my 44,100 samples per second, I actually require 16 bits per sample. Then calculating the size of a sound file. First of all, we need to know which sampling rate are we working with? If we are working with 44,100 sampling rate, means we are taking 44,100 amplitude readings per second, so that would be our sampling rate. Then we need to find out which sampling resolution we are talking with. Excuse me. So the sampling rate and sampling resolution are multiplied. The sampling resolution was how many bits I'm using to store each sample. Then we have to see, while are we recording to play on one speaker, or we are recording to play on two separate channels. The sound files you nowadays use, actually they are recorded for left and right, both speakers separately. Means they are recorded on a stereo. And in some old recording you might hear the single channel recording, the mono, which is the same recording being played through the both speakers. So if we are recording for a stereo system, we are recording to be played on two separate speakers. So we would multiply the result with 2, and then we would have actually how much space 1 second of the file is going to occupy. So this is also called the bit rate, means how many bits are going to be processed in 1 second. You can multiply that with the total number of the seconds. For example, if it is a 10-second recording, you would multiply it by the 10, and then you will find the total size of the file. And then you will have to actually adjust the memory size units. Means everything we have done from step 1 to step 5, that has been done actually in the bits. So now you have to actually divide it by 8 to convert it to the bytes. And then if you want to go to the kilobytes, divide it by 1024. And if you want to go to the megabyte, then again divide it by 1024. Let's look at an example of calculating the sound file. Using the same things that I have just mentioned, the sound I'm going to actually currently calculate is uncompressed. And the sample rate is 44,100 samples per second. The bit depth of 16 bits per sample, means the sampling resolution is 16 bits per sample, and we are actually going to record it for 2 channels of stereo audio. The mathematical calculation would be very simple. 44,000 into 16 into 2. It is going to give you how many bits you need to record 1 second of audio. In this case, it is 1411200. Excuse me. Then if we are going to record a 4-minute audio clip uncompressed, then I just have to multiply the number of bits that I have calculated to number of seconds that I have, which is 240. And I have the total number of bits that my file is going to require to store the data. Then, as I was telling you earlier, if I have to convert that into megabytes, I will first of all divide it by 8. Dividing by 8 would give me the bytes I have. Previously it was in bits. You know that bit is a single 0 or a 1, and a byte is collection of 8 bits. Then 1024, I'm going to divide the result by 1024, which is going to give me the kilobytes. and then again by 1024, which is going to give me the megabytes. So it roughly calculates to 40.37 megabytes of uncompressed audio according to the rules that I have just described here. This is the simple size calculation method, how we actually calculate the size of the sound file. If we are going to wrap this up now, sound is digitized using a band limiting filter and an analog to digital converter. An analog digital converter maps the sound wave using an time and amplitude graph, and those readings can be then digitized. Those coordinate points can be then digitized and stored in the computer's memory. To calculate the size of the sound file, we need to know the number of samples taken per second, which is the sampling rate, the sampling resolution, which is the number of bits used to store a sample, and the number of channels we are recording for. Stereo is 2, mono is 1. And we just multiply them and we get the total number of bits that we require. There's a worksheet on the way for you to solve. I hope that you solve and send it to me through email by the end of the day. If you have any questions, so now we are moving ahead to the question answer session. Thank you very much. Stay safe. Allah Hafiz.